And start recording. Boom. Okay, so where we left off, we just finished talking about Facebook's Haystack. Any lingering questions, anything you'd like to talk about from that little stretch where we did stuff? Nothing? Okay, so fine. So the rest of this is our intro to databases. So a database is basically digital storage for some kind of data. You can think of it as basically lists of things, whatever those things are. So, for example, Haystack is a database system for storing photos, right? But you could have database systems for storing invoices, for employee data, customer data, people who visit your website, any of that kind of stuff. You could, of course, have a database for it. Now, the database, of course, is just basically the file, the application that runs all that stuff. The database management system is all of the other stuff that goes along with that to make that database application usable. So basically the big things you're going to do with databases, number one, look at what's in there. Number two, change what's in there. Number three, potentially just store what's in there, put things in there to retrieve them later. And finally, restrict who can look at them and under what circumstances. Okay, so typical database operations, things like retrieving a photo, or Facebook context, or retrieving the set of users who have liked a particular photo, right? So when you click on that photo in Facebook, you'll see it, and then you'll see below all the, how many likes it has and whatever else, and that has to be pulled from a database in some way. And if you go to somebody's profile page and you say, hey, I wonder what you've been doing lately. You go to somebody's profile page on Facebook, boom, you see their like 2 weeks history of all they've done. And if they posted pictures, well, those pictures need to be available, at least as thumbnails, to show up on the profile. Okay, so things like that are what databases are for. We'll talk more about it. And there are two main approaches to databases. The first one we'll talk about is called relational, right? Often shortened to RDBMS, Relational Database Management System. And the idea with relational databases is you have structured data in the sense that all the data is in the same format. So if you have an invoice, for example, you would have a list of the customer and what the product was and what the date was and how many they got and what the total cost was and whether it's been paid or not. And all of that would be entailed in every invoice, right? So every record within that list would basically have the same format. NoSQL databases are a little different. And by a little different, I mean a lot different. They do still store data, so that much, they're still databases, but in a lot of ways, they get around some of the requirements of relational databases to do things, usually to do them a little faster or to more efficiently use storage media. But like pretty much everything, there's no free lunch, which is to say, it's not that relational databases are better or worse than NoSQL databases, but they're just different tools for different jobs, right? So if you have a wrench and a screwdriver, there's no meaningful way to say a wrench is definitely better than a screwdriver. But certainly a wrench is the better tool for, turning bolts and stuff, right? Same kind of thing. So different tools, different purposes, different usages. Okay. I don't want that anymore. Okay. So talking about relational database management systems, conceptually, your data in there will be stored as a set of lists called tables. And every table holds the same kind of data. So for example, Facebook might have one table of users that lists all the information it wants to keep about particular users. Might have another database of images that keeps, all the images it wants to keep, right? And it can have other databases for other things. But that's what we mean by a hierarchy of tables. Every table is just a set of the same kind of data. Now, each thing in a table, for example, each user, right, each line of user information or each image, that's what's called a row or a record. And it's called a row because when you write it out like a table, of course, each record is going to fill out a row. So, table is a set of records of a particular type. A row or a record is a particular thing of what's stored in the table, right? So if you have a table of photos, each record would be one photo. And then columns, or what I tend to call them fields, because fields is shorter, Fields are various attributes stored about each record in a table. So for example, suppose you have a photo. The columns for a photo might be the size, like 1 MB, 2 MB, whatever, the location where the photo was taken, and who actually ended up posting it to Facebook, right? So things like that could be the columns, could be the fields. Or for a user account, the fields could be the user's name, user's password, user's profile picture, stuff like that. Okay, so we understand tables, rows, columns. Hope it makes sense. Now, in a relational database, every table is composed of rows, and each row in a table has the same set of columns. Okay, so when you draw it out, it looks like a grid because every row has the same columns as every other row in that table. Okay, and here's an example. So here we have a list of, let's say these are Facebook users, and every Facebook user has a name, has an email, has some kind of password stored in there, has a record of their birthday, and some link to their profile picture, right? Some scrambled key that says, here's where you can go to find their profile picture. All right. Okay. Now there are 4 basic database operations. Number 1, insert, right? Adding a new record to the table. For example, somebody joins Facebook, boom, they're a new user, you need a record of that user in your system. So to the table of users, you add a new record for that user. Delete is the next one. Sometimes you got to get rid of data. For example, somebody says, oh, I'm done with Facebook, I'm out of here, delete my account. At some point, Facebook will dig through all their stuff and actually delete their records, right, from whatever tables they're in. So you need to have that. Modify, of course, changing data within a record. For example, suppose you grew up in Milwaukee, but you moved to Chicago to come to college here. So you're changing your Facebook account to show that your current location is now Chicago, right? That's what a modify operation is. You go into the database and change something. And the last one is querying. Querying is simply retrieving data. So you can think of it like a query is often used as an equivalent term for a question. Well, a query for a database, you're asking the database, hey, what about this? And you hope the database can give you the answers. Now, queries are very, very important because typical databases read a lot more often than they write data. So think of the case where you're uploading a photo to Facebook. You upload it once, right? But it could get viewed dozens, even hundreds of times, maybe thousands if it's a popular photo, whatever. So because of that, like we talked about back with RAID systems, you can optimize your systems to write faster or read faster. Well, Facebook in general wants to optimize its photo storage in order to retrieve photos faster because it's going to do it so many more times. Interesting thing about relational databases is that queries can also span across tables. That's what we mean by saying, it's a relational database, is that there are relations built in between tables. So, for example, if you had a table of photos and every photo had associated with it some user, and you had another table of users and every user had associated with them where they're from, then you could run queries like retrieve the complete set of photos viewed yesterday by users from Chicago, right? So you have a list of who all viewed what. You have a list, you can find out who are the users from Chicago, and you can basically do the intersection of those two things, right? So you can set up those kind of multi-table queries, and they're very useful. Especially since if you didn't have that, you would have to store all of your data in one very, very, very absurdly large table. Just saying. Okay. We'll have more to talk about relational stuff in a moment. Now, structured query language, or SQL, is the standard language for how all of these database operations are coded. What you see in practice, actually, I guess I'll mention this because people do ask. So you have a database here. Excuse me. And you write some code in SQL. Could be something like select all, that's a wildcard asterisk, from, I don't know, users where I don't know, name equals Doug. Okay? You find all the Dougs in your database. Now, this code by itself, this isn't really going to be able to do anything, right? This little snippet of code, it doesn't understand where the database is located, how data is arranged in the database, any of that stuff. So you need some kind of basically intermediate code, maybe some, database application that accepts this instruction and knows where the stuff is stored and how it's actually stored and where to get to it. Okay, so SQL code by itself isn't going to be able to do all this database stuff. What it is there's a database application that understands SQL and also understands where all the data is actually located. Okay, in case you were wondering. But you'll get some of this in the labs. People my age and younger generally pronounce SQL as SQL. People my age and older generally pronounce it SQL. Okay, so there's definitely, I'm like right on the cusp of I could have tipped either way on that one, but I've gone with saying SQL. I used to say SQL. But I'll mention it's probably unwise to correct anybody about that, right? So like if you're in some kind of job interview and you're getting interviewed by some, 65-year-old dude who's been doing databases for 40 years, and he asks you, oh, well, what do you know about SQL? And you'd be like, well, first of all, I know it's pronounced SQL, right? I mean, you're not gonna make any friends doing that, just saying. Okay. Anyway, SQL has command groups for things like queries, for various types of data manipulation, like if you're adding records, deleting records, modifying records, managing data structures themselves. If you want to create a new table or add a new field to a table, right? SQL has ways you can do that. And finally, data control language for managing permissions, right? This is very important in real-world databases because it very, very, very often happens that users only have access to part of a table. For example, I work at UIC. We have a database system that has all of our payroll information. So if I want to know when I'm going to get paid and how much I'm going to get paid, I can go in there and look at that, right? And all that information is stored in, I would assume stored in one big table for all the employees. But of course, they don't want me to go in there and look at anybody else's information besides mine, right? So there's some sort of permission management in there where it says, okay, Doug has permission to access his own information in the payroll table, but he doesn't have permission to access any other records. All right. Now, key fields. Let's talk about key fields. So one of the things you want to do, okay, back up a second. When you're doing queries in a database, it is very important that your database can only give you one answer and that answer is the correct one, okay? So I'm going to put something up here. All right, I'm going to edit this a little bit. Yeah, I'm going to get to it. It's fine. All right, so I'm going to replace this one. I'm going to replace Charlie Chupacabra here. Okay, and he'll have a different email, cc4 Yahoo. Okay, and whatever else he has for his other stuff, we don't care. We'll give him a password 1 2 3 4 5 6 7 8. Okay, now suppose Charlie Chupacabra tries to log into the system, and he types in his email as cc3@yahoo, and he types in his password, right? The system's going to be able to look up and say, oh, I'm going to scan through this table, find the email that matches what you put in, and then I'm going to scan through the table and see if the password you typed in matches the password that gets stored. Make sense? Okay. Same thing, if CC4 Charlie Chupacabra shows up, same thing, right? It's going to see his email and this. But what happens if they both use the same email? What if you have two guys that use, she's not going to be Charlie anymore. She could be Christy. Okay? She's Christy Chupacabra. And she has the same email because she and Charlie, they're twins. They still live together even though they're 25 because twins sometimes, whatever. None of my business. But they use the same email in the system. Okay? And so when they type in the email, you don't know for sure which password is going to be the one that gets read. Right? Now, you might say, well, it's got to be the first one because it's first in the list. Maybe so, right? But you don't know how the different copies are stored or where they're stored or how the actual scanning process is going to work. So just from the way the data is stored, you don't know. But what you do know is it's going to be one or the other, right? So half the time they'll enter in their email and their password and they won't be able to get in because, you know, the system's going to look at the wrong one. Does that make sense? This is a problem, right? We don't want that to happen. How do we do that? Well, we make this email a key field. So I'm going to put in big letters, key. And when you have a key field, you say every record, every entry in this column has to be different within the table. So you can't have two CC3s at Yahoo in this table, right? One of them will have to go back to being CC4. And that's the key value requirement, is you say there can't be duplicate values in a column. The reason why you do this is so that you're always sure that your database is looking at the thing it's supposed to be looking at. Okay? Questions on key fields? Any of this not make sense? All right. So, excuse me. Now, again, that's the point. By having a key field so that we ensure there's a unique value in every record in a column, we also make sure that there's some distinction between every record in the table. You can't have two totally duplicate records in a table. So, key field never duplicated within a table can actually encompass one or more fields. You can have multiple fields as a key. So I'll give you an example of that. In Google Analytics, right, which is a web analytics platform, if you have a website, you can install Google Analytics on it, and then Google will track all site data, like who visited your site, what they did while they were there, that sort of thing. That's what web analytics is. And there's a concept in Google Analytics called a unique event, a particular thing that you're tracking that somebody does. And a unique event involves a triple entry of three things. Number one, the particular visitor. Number two, the particular session. So, you know, basically what interval they were at your website in. And then number three, the event itself. So when an event happens on the website and Google's tracking it, they say, okay, let's look at these three things. If they find an identical match, the same user during the same session doing the same thing, like you click twice on an image or, you know, on a thumbnail, something like that, it's not going to be treated as a unique event. Google's going to say, okay, we already have a record for this thing, so the second one, we're just going to up the count on it to show it happened twice. But if it's a different unique event, for example, a different user or the same user in a different session or the same user in the same session doing a different event, Google's going to create a new record in that database with the initial count of 1 to show that that unique value happened twice, or to show that unique value happened for the first time. So anyway, the key value in that case is those three things, the user and the session and the event. And those three things together make sure that every record is unique. Okay. Now, anytime you have a key field and you create a new one, like for example, you go to Facebook and you create a new account there and you try to reuse your old email, you should get a warning message that says, you can't use this email. This email already exists in Facebook as an account. Please choose a different email, right? And the reason is that very same email login process I was talking about, okay? Facebook wouldn't know if there are multiple users with the same email. Facebook wouldn't know which one's password to use. For that matter, it wouldn't know which one's data to bring up. And anytime you create a new one or you modify an existing entry for a key field, the database, well, a well-designed database should go through and check to make sure that you haven't violated that uniqueness constraint of key fields. Okay, so if you already have your email and you want to change it back to something else, then of course, again, Facebook is going to look and make sure that nobody else is using that email. All right. Now, you also have a concept of a foreign key. Now, I'll mention this here because it's one of the things that gets mentioned in the lab exercises, and I sometimes get emails saying, hey, we never learned about foreign keys. I'll always say, well, yeah, you did. It was just in lecture, and you must have been out that day or whatever. Okay, but foreign keys, it is a thing that we'll talk about. So, suppose you have a list of users and a list of cities. All right, so we'll have one table of people, right? We don't really care what they're doing, but for table, you have the fields name, email, and zip code. Okay. Then we have another table for, we'll call it zip codes and municipalities, basically cities. Okay, and in there we have the fields zip code and the city. Okay. Excuse me. So first person is Joe, and Joe has whatever email he has, right? j@j.net. And Joe's zip code, he lives in Chicago, 60601. Okay. And we have table here, 60601, which we know is in Chicago. Okay, and 60602, also in Chicago. And we'll do a Rockford one. 61103 is in Rockford. Okay. So this record, let's box them both. Corresponds to this entry. So zip code is not a key field for this table. People. Why wouldn't it make sense to have zip code be a key field for the people table? Why would that be a bad idea? It's highly probable that you'll have multiple people in the same zip code, right? Wouldn't make sense to have that be a zip code. Wouldn't make sense to have that be a key field, right? Okay, so because of that, you don't want zip code to be a key field on table. It makes more sense to use email, right? You also probably wouldn't want Joe to be a key field for your table because it's very possible you could have multiple people with the same name, Joe. Every now and then, every few years, I have a class like this where I have two students in the same class with the same first and last name. So yeah, it happens. However, zip code does make sense to be a key field over here, right? Makes a lot of sense. Key field, because for any zip code, the city will be known. Not true that if that for any city, the zip code will be known, right? Because in a big city like Chicago, you can have literally dozens of different zip codes. Even Rockford, I don't know exactly how many it has, but like probably 5 or 10. I know it has multiple zip codes. So it wouldn't make sense to have city be the key field. Zip code is the key field for this one. Now, zip code over here is a foreign key. Zip code here is a foreign key because it is a key field in its own table, right? It's not a key field for people, but it is a key field in the table zip codes and municipalities. That's what we mean by a foreign key, okay? And this is how relational stuff works. By the way, I'll mention this as a last thing. Relationships between tables. If you want to find out Joe's city, you can find the entry in zip codes and municipalities corresponding to Joe's zip code. Okay, so that's how you do it. You say, oh, Joe is in zip code 60601. The application will scan through this table of zip codes and municipalities, find that zip code. That city value on that same row is going to be the one that gets pulled, and the database can tell you Joe lives in Chicago. Okay? Questions? And you'll do some of this stuff in the lab, right? You'll do much more than this, that's for sure. Okay, not necessarily this week. This week, I believe you just build up a table, put some data in it, get used to actually using Access. You'll do some more interesting stuff later, like queries and relationships and calculated fields, things like that, over the next few exercises. Okay. Anyway, like I said, if you have questions, feel free to shout them out because we're not real fussy about formality and stuff here. Okay. Next thing, atomicity. Right? So for any of you that have taken any level of physics or just have some like baseline science knowledge, you know that once upon a time, people called these little chunks of matter atoms because they thought they couldn't break them up. They thought that they were the tiniest, most indivisible pieces of matter that there was. Turned out to not be true, right? But yeah, that's what they thought, so the name stuck. In terms of databases, atomicity means each database field holds only one element. You don't have a cluster of related things within the same field. And the reason why you do that is because, again, we always want our databases to give us the right answer and therefore for there to only be one answer to any question you might ask it. So that's what I mean by saying it removes ambiguity from the database. There's not going to be a way where you can get multiple or unclear answers. So, simple example. Suppose you have a database with multiple phone number possibilities, right? You have one field for your people and it's just called phone number, but you can have an unbounded list of how many phone numbers you put in there. So you could put in your old number, your current number, your day phone, your night phone, your work phone, your home phone, your cell phone 1, 2, and 3, plus your landline, right? Plus, I guess if you want your like backup number to your mother-in-law or something, I don't know. You'd have a whole list of phone numbers in there, right? But the problem is, if somebody is checking that database and say, hey, I want to find Joe's phone number, they're not going to get just one phone number, are they? They're going to get that whole list. And they'll have the question, gosh, which one do I call? This is a problem, right? So it's a problem in terms of that, just in terms of ambiguity in the data. It would be better to set up all of those phone numbers in separate fields. For example, have one field for work phone, one field for home phone, or one field for night phone, one for day phone, that sort of thing, right? So you say, oh, it's nighttime, I want to call their night phone, or I know they're at work, I want to call their work phone. Then you can get what you're looking for. Okay. The other thing that's a problem, talk about that in a moment, is this. It's not immediately clear that this is a problem, but we'll get, there is a problem with efficient use of storage media capacity if field formats are too variable. All right, we'll talk about that in a minute, but that's the other thing, and potentially arguably much more important in some cases, sure. Now, relational database models are typically going to assume all fields are atomic. Okay, if there's going to say, well, this is the field I'm looking for and this is what's there, that's just what's there, right? So anything that exists in the database should have exactly one place. And the nice thing about this facilitates uniform data format. So for example, typical American phone number, 3-digit area code, right? And then 3 digits and then 4 digits. That's the typical phone format. So you know your database has to keep 10 numeric characters for every phone number, which means at the very least, you can prevent the possibility of people entering a non-numeric character or not enough digits or too many digits, right? So there's various ways that can help reduce the potential for errors. If your field is unbounded and you just said, well, here, have like 256 text characters, enter in as many phone numbers as you like, right? It would be entirely possible to put in some overlong or overshort phone numbers or omit the area codes, things like that. Excuse me. Okay. Having said that, assuming something is atomic doesn't mean it's going to be enforced. So let's roll back up a couple slides here. This one, for example, now name could be split up into last name and first name, right? That would make sense for a lot of applications. But it's not necessarily going to solve all your problems. So take a name like Albert Anderson, right? We can look at that and say, yeah, Albert's probably the first name and Anderson's probably the last name. You don't know that for 100% sure, but yeah, that's what we'd expect. But the database isn't going to know that. The database has no idea, right? So even if you broke those up into last name and first name, it is entirely possible that you could have somebody with the very oddball last name, Albert Anderson, with a space in between them, right? There are people who have spaces in their last names. So, you know, when we say last name, first name, if we split that up into two separate fields, that's kind of on the user, on the system manager, somebody to figure it out. The database can't do it all by itself, right? The database doesn't have any way to parse these names and say, oh, here's a last name, here's a first name, and I definitely know that's going to be true. Because then as soon as you do something like that, you're going to find somebody who works at your place whose first name is Anderson is going to wreck the whole system. Okay? All right. Anyway, another problem that often happens in databases is conflicting data. Conflicting data can happen because of dependencies. So, for example, one dependency that's very common is that age depends on someone's birthday. So, if you had in a record both someone's birthday and someone's age as separate entries that are permanently stored, it would be very possible to make a mistake on one or the other when you're first setting up that record, right? You could say something like, oh, this person was born in what, 1952, and so they should be 71 years old. But when they typed in their age, they made a typo and just said they're 7 years old, right? There's a conflict there. So, you know, if they're looking at their birth date for an application to see if they're old enough to buy booze, then they would be okay to. If they look at the age value to say, are you old enough to do this? Because, you know, when you go to a website about booze, right, they'll ask you if you're 21. And then, I don't know, depending on your age, you either tell them you are or you lie, but, you know, they're going to ask. Anyway, likewise, city and state depend on zip code. So if you know what zip code someone's in, you definitely know the city and state, because that's how that works. For any zip code, it's, you know, unique for one municipality. However, if you know somebody's city and state, you don't definitively know their zip code, right? At best, you can narrow it down to a set of options, right? There's like so many zip codes for Chicago, it's got to be one of them. But what you could have, if you keep these things in the same record, the problem that could happen is, you know, when you're creating the record, you enter in the zip code with a mistake, or you enter in the city with this mistake, right? Imagine if you're typing in the zip code and you make a mistake there, or you type in Chicago and, you know, instead of typing Chicago, you add in like 2 C's or something, and you make a mistake there. So there's various sorts of input checks you can do with that. Like you could, you know, you could run through it some filter that says, okay, let's make sure that this zip code and this city pair is one that actually exists in our databases. And if it doesn't, you say, well, no, you made some kind of mistake, right? But if you put those things in the same record and you don't do some kind of check on that, right? Suppose somebody's entered in the zip code correctly, but not the city name correctly. If you have a query that's looking for all the people in Chicago, that person's not going to show up, even though he's in there, right? Likewise, if the city name is entered correctly, but the zip code isn't, you do a query for the city, that person will show up, but you do a search based on the zip code, and they won't. It's a problem, okay? All right. Anyway, so yeah, those are kind of common conflicts. And the solution, the way that is typically handled, is you simply remove dependencies from the table, right? So for example, instead of storing zip code, city, and state in one table, you could store a zip code in the table with the person's data and have a separate table for storing the zip code and city combination, like I did in the example I just had up a little bit ago. Okay. Questions on any of that? Would anyone like to know more? Okay. Well, next thing, metadata. So, metadata is data about the data. And that can entail, that can be in a variety of forms. So number one, simple things like the names of the data, the tables and the columns, right? The database doesn't care what you call a table. It could be called people, it could be called employees, it could be customers, whatever. The database really isn't going to care. You write your SQL code to say, hey, give me all the stuff from this particular table named this, and it'll work, right? But the database itself really doesn't care. Other things like the kind of data you can store in a column. For example, different kinds of numbers like integers versus floating point numbers, right? Ones with a decimal, or time or date formats, or unformatted text. Those are all possibilities you can have. And so that's more of a presentation issue. but it can be a formatting issue. For example, if you're saying, well, give me your standard short date as, month and day and year, and then the things that the user enters into the system have to line up with that somehow, right? Like you couldn't put in the month as being the 15th month because that's just not going to happen. All right. Other things like the format of the data itself, right? So things like the maximum value or minimum value, maximum length, like you might say a password has to be at least 12 characters, or if you have a number, a floating point number, the number of decimal places, things like that. Now, relational database standard practice is a column has the same data type and the same format for every record in that table, right? So if you have, for example, a table of people and you're listing keeping their birth dates in that table, every birth date would be in the same format, whatever that format is. I'm going to show you something. I'm going to show you why they do this. So once upon a time, okay, efficient use of storage media capacity of field formats are too variable. This is, we're back to this. I'll put it in orange now. Okay, so suppose you have records for employees with 100 byte length, all right? It's 100 bytes of data. And some of it's the last name. So last name, let's say, is 20 bytes. And first name is, let's say 12 bytes. So we have to do 32. Address, let's do 40 bytes. Brings us up to 72. Email, we'll do 18 bytes. And then phone, we'll do 10 bytes, which, if my math is correct, brings us all up to 100 equals 100 bytes total. Okay. And remember, since this is a relational database and every record has the same format, every field within the table has the same format for all of its records, every record will occupy 100 bytes of space, even if the data doesn't fill it all. Okay, so even if your last name, like say Lundquist, is only 9 characters long, well, those empty 11 characters are just gonna all be zeros in this database. Okay, or if your first name is Doug and it's 4 characters, then those other 8 bytes are just gonna be empty zeros. All right, so that's the way this relational database is gonna work. Now, why do they do that? Why? This is advanced topic, okay? Advanced topic will not be directly asked on exams, but still good for understanding. You might say, hey, why do relational databases enforce this property of having, the same field size within a table? Okay, reason is, if all records have the same format, looking up data is very fast because you only have to do multiplication and addition, not scanning. So what I'm saying is, imagine if you're doing a query for email equals j@j.net. Okay, the emails will start with an offset of 20 plus 12 plus 40, right? All 3 of these fields that precede it, right? And then the email is going to start after that, equals, what is that, 72? 72 bytes after the start of the record. So since each record is 100, as you're scanning, you could say check, 72, then 172, then 272, then 372, etc. Right? So you don't need to scan through the entire record and find out where email starts and then check email. You just say, I know I just got to look in this one place, got to look in this one place, got to look in this one place. And if the records are large and the tables are large, this approach saves a lot of time, right? It really saved a lot of time in the 70s and 80s with the shitty old hardware they had back then. We were glad to have it, but still, right? Nowadays, even if you have pretty inefficient searches in fast RAM, it can be pretty fast, but this is still going to save a lot of time. It's going to save a lot of workload, if nothing else. It'll save on your electricity bills. Okay, does this make sense? Why we do offsets, why that's a nice property? This is why relational databases do that, why they say, okay, everybody's address in this table is going to be a max of 40 bytes. Everybody's email is going to be a max of 18 bytes. They do it so things are easier to find. Now, problem often happens that you have data with wildly divergent sizes. For example, suppose you're on Facebook and you're storing images, right? So we'll talk about that. Suppose you are Facebook storing images with a maximum size of 10 megabytes. Okay, you say, well, this is the max we're going to allow. But suppose further that most images are only about 1 megabyte. Okay? What does that mean for your system? What does that mean for your system? Sorry, a little, what? Exactly. It's like buying a really big house and just living in the kitchen. Okay? So yeah, this for your system means that circa 90% of your storage capacity will be wasted, right? Because if you have to allow 10 megs for every photo, because that's the property of a relational database. If you say this is the max, that's going to be there for everybody, but most of the time you don't use it. And so even though storage isn't super expensive, paying 10 times more than you need is pretty wasteful, right? Facebook's not going to do that. So they seek a different approach. And NoSQL databases can handle this. Remember when I said NoSQL databases allow cutting some corners on these relational database properties so that they can do some things a little bit better? Well, one of the things that you can do a little bit better with what's called a document storage system is you can pack the documents in tighter. If you say, for example, suppose you have photos and you say, I know that nobody is ever going to make this photo bigger or smaller than what it is, so I don't need to worry about that. You can just pack photos into your storage media, one right after the other. So as soon as one record stops, the next record begins. And it's not going to be quite as fast as a relational database, but it might be fast enough. And it's going to be way better in terms of storage usage, right? Because your disk drive is basically going to be packed full of photos instead of being 90% empty space. All right. But we'll talk more about NoSQL databases too before it's all over. All right. So just a few more slides. So quick discussion here. Relational databases, remember, it's like the wrench and the screwdriver, right? They're good for some things, not so good for other things. So they are very efficient when the data is stable, right? When things don't really change much, relational databases are probably great. In particular, fields are homogeneous for individual objects. That means pretty much the same, okay, homogeneous. So if you say everybody's name, you know it's going to probably be in that range of like, 10 to 40 characters max. Yeah, there's a little bit of wastage there, but it's not going to be huge. If you know everybody's phone number is exactly 10 digits, then there's no wastage, right? You can just allot that 10 digits worth of space for it. New fields are not added very often, right? One of the problems with a large relational database is it takes a lot of careful calibration to put the popular data in one place and less popular data in another place and regulate the frequency of calls to it so you make sure that everything gets delivered about fast enough. There's a lot of calibration work involved in making sure your database is set up well. Anytime you add a new field, that's going to fuck all that up and you're going to have to redo it, and it's a whole lot of work, right? So you don't want that to happen very often. Yeah. So the cons of relational databases, number one, not very flexible, right? It's hard to change the database schema, by which we mean the general way in which the data is stored and ordered and organized and what storage media it's kept on, all stuff like that. It's hard to change that database schema while still maintaining the proper relationships between tables and still maintaining performance. Number two, in many real-world cases, you can't find an easy, simple, efficient schema for what you're doing. So, simple example, suppose you have a database table full of invoices, right? Now, suppose your invoice, the max number of items on an invoice could be 100 items that somebody bought. So if you had a relational database, you'd need to have 100 fields in every record for what people bought. But the vast majority of invoices are probably going to be pretty small, like around the range of like 1 to 5 items. People tend to buy stuff in small quantities. So again, just like the thing we had with the big images, you'd be wasting a lot of space. Every record would allow for, 100 items, but most of the cases they're using 1 to 5. You're wasting like 95% of your database capacity. Okay, it's not very good. Finally, last thing, relational databases. This whole thing about offsets working in RAM, that's really a RAM thing, right? If you have to find stuff on disk, you're going to have to kind of scan through the whole disk anyway. And you could get a little bit of efficiency with knowing where the data is, but it's not going to be that big of a deal. The big deal is when you have all this data stored in RAM, you know exactly where to go to find it. But if you're running some kind of system where your database tables are so big that they have to be stored on different pieces of hardware, then there's going to be a lot of cross-checking back and forth. You say, well, I'm looking for this one thing, its partner is in another piece of RAM on another device, and then these operations, instead of happening in microseconds at RAM speed, they're happening at milliseconds at network speed, a lot slower. Okay, very quickly, I'll get through this in a minute. So NoSQL systems, you don't need to memorize these. These are just some examples if you want to look up a little bit about what these are about. Mongo's document storage, Cassandra, Facebook used to use that for instant messages. They've since released it as a public open source software. And another one, Apache, Hadoop, you might have seen that for large scale number crunching. So simple example with how this works, right? This is again an example, specialized system for a specialized problem. Imagine if you have a massive pile of photos and you stack them all up physically as photos, and on each one who actually posted it, right? If you run a query that says, show me all the photos posted by Joe, you could run that query on that one stack, and the results would be whatever they are. But you could also take slices of that stack, hand them out to different people, say everybody gets a slice, scan through that quickly, tell me the ones that have Joe, and recombine those results at the end, and the results would be the same, right? So that's what this MapReduce is. You have a very big task that would take a long time to run on one device. Instead, you slice it up into slices that are the equivalent of the entire task, but you give one slice to a different piece of hardware, so you can run thousands or tens of thousands of those small operations in parallel, recombine the results at the end. The network is actually, the same, a little bit bigger when you allow for the, the slicing and the recombination, but you get the results back way, 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 way faster because you don't have one machine trying to go through that huge whole stack of work. Okay? All right, that's it. That's all I got. We'll see you next time. We're going to go in on that Facebook feed, so please read the document, the lecture notes for it. All right. Okay.
So you mentioned that the deadline for all the homework assignments was Wednesday.
Well, there haven't been any homework assignments to speak of yet. If you had a lab today, yeah, I mean, we'll cut you because the lab shells aren't up. I've requested them. Hopefully, they get back to me today.
All right,
Yeah, yeah, no worries. Yeah, hello.
Coach, you said that we would start worrying about packback on week 3.
Yeah, I'll talk about that Wednesday.
All right, perfect. Thank you.
Yep. Hello.
I have a question about